Now we're going to look at what's known as polar effects. And these are more remote effects in the molecule. So basically, what we're going to be looking at still is some molecule bonded to an atom, bonded to a hydrogen. We're going to be looking at the acidity of the hydrogen. But in the comparisons we make here, now the atom A stays constant. And what we're going to be looking at instead is analyzing how nearby structural changes affect the acidity. The first remote effect we're going to talk about is something we started this chapter with, and that is resonance. And just keep in mind, resonance stabilizes everything. So in terms of how we're going to apply this to acidity, if you have a negative charge on a conjugate base that is spread over multiple atoms through resonance, it's going to be more stable. So put more clearly, if a negative charge on the conjugate base is delocalized over multiple atoms, it is stabilized by resonance. A more stable conjugate base comes from a stronger acid. Right, so let's look at a couple of examples to compare. Here are two acids we want to compare for acidity. Now remember what I said before about the atom, the protons bonded to remaining constant here. And that's exactly what we have. The protons bonded to an oxygen in both cases. We're looking at something more remote in the molecule. So what you want to do is think about each of these reacting with a base. And if you want to draw in your curved arrows, you can. The base will take the proton and put a lone pair on the oxygen. I'm not going to draw in all the lone pairs, but we add an extra lone pair to that oxygen and it gets a negative charge. Do the same to this oxygen, it gets a negative charge. Now if you compare both of these, the one on the top, that negative charge is stuck on a single oxygen and it's localized in that position. In comparison, on the one below, this negative charge, or more technically the lone pair, we can push it here to form a double bond and push this pi bond up onto the oxygen. And we can draw a second resonance structure. So this negative charge is delocalized over 3 atoms. That means the conjugate base here is more stable compared to the less stable conjugate base up here. The more stable conjugate base comes from the stronger acid. In this example, we're comparing, these are known as alpha protons that are next to a carbonyl. And just like before, the atom that the proton's bonded to remains constant. It's a carbon and a carbon in both cases. So this must be a remote effect that we're comparing. So now think about reacting each of these with a base such that you draw the conjugate base. Here, the conjugate base gives you a lone pair and a negative charge on the carbon. Here, it's very similar. You get a lone pair and a negative charge on this carbon. Now, you might just look at this and say, well, both of these have resonance, so how can we make a comparison? This one has a resonance structure. Like that. This one down here It's very similar in that we can move the electrons to the carbonyl, drawing a resonance structure. But what you want to spot is there's more resonance in this second example. You can also move this negative charge toward the other oxygen. So there's a couple ways to think about this. Probably the simplest way is just to say more resonance, more stable. A more technical way to think about this is, how many atoms the charge is delocalized over. In the top conjugate base, the charge is delocalized over 3 atoms. In our bottom conjugate base, through our resonance structures, the charge is delocalized over 5 atoms. So that means that conjugate base is more stable. The negative charge is more spread out. More stable conjugate base tells us this is the stronger acid. The next effect we're going to talk about is called the inductive effect. And what the inductive effect is it's when nearby electronegative atoms stabilize a negative charge by withdrawing that electron density through the sigma bonds. So a way you can kind of think of this, let's just say you have a carbon with a negative charge, and maybe there's a nearby fluorine. So what's going to happen, that fluorine is going to pull that charge through these sigma bonds towards itself. So it's not resonance, but it's kind of similar in that it helps spread this charge across multiple atoms. So let's look at a series of compounds and we'll see how the inductive effect plays a role in their relative acidity. All right, so here we have several compounds, and in all cases, the acidic proton is the one on the oxygen. And what you see is that the atom that proton is bonded to remains constant in all cases, which is important for these types of effects. So now if we start going from left to right and see what happens structurally, well, in the first compound, there's no electronegative atom other than the oxygen, which is consistent in all of the cases. But in the second one, we've added a nearby electronegative chlorine. Then the next one on the list is even more acidic because the chlorine is closer to the acidic proton. On this one, it's 2 carbons away. On this one, it's only 1 carbon away from the OH. On the next one, we switch from chlorine to the more electronegative fluorine. So that increased electronegativity of the atom enhances the acidity. And then finally going from 1 fluorine to 2 fluorines. Now we're just kind of doubling up that effect. So that even further enhances this inductive effect. Now some of you might be saying, well, wait a second. We talked before that HCl is more acidic than HF because of atom size. So why are you now saying that the more electronegative fluorine is more acidic? It's all about where the acidic proton is bonded to. In this case, this is an inductive effect because the acidic proton is on the oxygen. That atom doesn't change. So in this case, it's an inductive effect that electronegativity matters. For the size effect, it's only when the hydrogen is bonded to an atom changing size. So in the case of HCl versus HF, here's the acidic hydrogen. It's directly bonded to an atom changing size. In the examples up here, the acidic hydrogen is directly bonded to an oxygen. That doesn't change. So now the halogen is just a remote inductive effect. The final polar effect revisits something we talked about in the previous chapter, and that's hybridization. And what we're going to do again is apply this in terms of S character. So let's review what we know about S character. More S character means electrons lie closer to the nucleus. That means the electrons are held more tightly. More tightly held electrons means more stability. And in terms of acidity, that means stabilization of the conjugate base. So you can apply this to any atoms that are changing hybridization. For this example, let's just look at an alkane, alkene, and alkyne carbon. If we compare these three, the atom that the hydrogen's bonded to we're looking at is a carbon in all three cases. So that atom does stay constant. But if we think about its hybridization, in the alkane, that carbon is sp3, which means it's 25% S character. In the alkene, it's sp2, meaning it's about 33% S character. And then in the alkyne, it's sp, meaning it's 50% S character. So of these, the alkyne CH has the most S character. It's the most acidic. The alkane is the least acidic. You can think about this as well in terms of the conjugate base. Here's the conjugate base of the alkane. Here's the conjugate base of the alkyne. Because of the S character, this is a more stable negative charge.